force, a moving object will A, slow down and eventually stop, B, stop immediately, C, turn right, D, move with a constant velocity, and E, turn left. This all goes back to an object in motion will stay in motion, an object at rest will stay at rest unless acted on by external force. That's Newton's first law. So if there's no net force, then it's going to keep moving the way it was moving. So D. When a cat sleeps on a table, the net force on it is A, 0, B, directed up, C, directed down, D, directed in the horizontal direction, or E, more information is required. Remember, net force is all the forces added together. And if the cat is on the table, it's not sinking in the ground, it's not rising in the air, so the net force needs to be 0. And if you think about it, we've got energy down on the cat. And since it's not going anywhere, it's just sleeping, Fn is up, and they need to be equal, which would make net force, when you subtract them, 0. When the engines on a rocket ship in deep space far from any other object are turned off, it will, in this case, D, move with a constant velocity. This is the same thing, where we're using Newton's first law. There's no force there. It's still going to move with a constant velocity in space. Number 4. In order for a rocket ship in deep space far from any other objects to move in a straight line with constant speed, it must exert a net force that is. So if you remember, we said we want it to have a constant speed, constant velocity, and we just said in the last problem, if we look back, that the object is the forces are turned off. So that means we need a 0 force for it to stay constant. Number 5, if a book is on the dashboard of your car suddenly and it flies toward you, the forward velocity of the car must have A, decreased, B, increased, C, change direction to the right, D, becomes 0, or E, change direction to the left. So if you think about it, when you're in the car and you have the book there, the stuff flies back at you when the car speeds up because the book is not moving as fast as the car. And it's staying at rest. 6. Which Newton's law can explain the following statement that we often see on the highway display? Buckle up, it's the state law. Well, we've just been talking about an object in motion will stay in motion, an object at rest will stay at rest. So if you're in a car accident and the car is moving and you get into an accident, the car suddenly stops, your body is still in motion, so you're going to fly out. That would be Newton's first law, and that's why you should wear a seatbelt. Number 7. A spacecraft travels at a constant velocity in empty space, far away from any center of gravity. Which of the following is true about the force applied on the spacecraft? A, the applied force is equal to the weight. B, the applied force is slightly greater than its weight. C, the applied force is slightly less than its weight. D, the applied force must be perpendicular to its velocity. Or E, no applied force is required to maintain a constant velocity. Again, this comes down to the whole Newton's first law, object at rest. So if it's staying in a constant velocity, there's no force added to it. Number 8. A boy rides a bicycle at a constant velocity. Which of the following about the net force is true? Again, these are the same questions over and over. We know the net force is 0. It's at a constant velocity because if you have sigma F equals ma, it's constant velocity. A is 0, which means this cancels out and equals 0. So your net force equals 0. 9. This is all like personal experience for you guys. So you're standing in a moving bus, facing forward, and you suddenly fall forward. This can be an indication of the following. The bus speeds up, the bus slows down, the bus doesn't change its velocity, the bus turns right, the bus turns left. So again, this is that whole thing when you experience it, and usually when you're standing there, your body is moving forward. You're in that object in motion, and suddenly the bus slows down, but your body didn't catch up. Your body's still moving forward, which is why you fall forward. Now this one, it's the same thing, but now that you fall backwards. So if you're falling backwards, that means that the bus is speeding up for you. Okay, same thing. Now you're falling to the right. So this means the bus would be turning to the left. As the bus starts turning to the left, your body's still kind of going straight. So now when it turns, you start going to the right. All right, the acceleration of an object is proportional to A, the net force acting on it, B, its position, C, its velocity, D, its mass, or E, its displacement. If we have our equation sigma F equals ma, proportional means that if one went up, then the other one would go up as well. So if acceleration goes up and mass stays the same, that means your sigma F is going to also go up. So that would be net force. The acceleration of an object is inversely proportional to the net force, its position, its velocity, its mass, or its displacement. So now if we have our equation over here, obviously we know velocity is not in there, displacement's not in there, position's not in there, so it's either force or mass. So if acceleration goes up, well, what does mass do? If we get mass by itself by dividing by A on both sides, so now we have sigma F over A equals mass. If acceleration goes up, that means you're dividing by more pieces, which means that your mass would get smaller. So they are inversely proportional. 14. A net force F accelerates a mass m with an acceleration A. So this is one of those ones where you're going to start with the equation and see what happens. The same net force is applied to mass 5m, so sigma F's not changing, but your m is changing. We want to know what happens to the acceleration. So the first thing we should do is get the acceleration by itself. So we need to divide by m. Now we've got A equals sigma F over m. And now they're saying what happens when it's 5m. We've got our sigma F that stays the same, but now it's 5m. So if we look, it's A cut into 5 pieces because you're going to have to divide the answer by 5. So A over 5. All right, next one, a net force, again, acts on a mass m and produces an acceleration a, so they're just talking sigma F equals ma. So now they want to know what happens to the acceleration if the net force changes to 3F and the mass changes to 6M. So let's get A by itself again. So A equals sigma F over M. And now they want it to be 3 sigma F over 6M. And if you reduce 3 over 6, you get 1/2. Which means your A is now going to be divided by 2. A loaded truck collides with a car, causing a huge damage to the car, just falling through about the collision. The force on the truck is greater than the force on the car. The force on the car is greater than the force on the truck. The force on the truck is the same in magnitude as the force on the car. During the collision, the truck makes greater displacement than the car, or during the collision, the truck has greater acceleration to the car. If you remember, Newton's third law says that it doesn't matter about the mass. Two opposing forces will have, if one object acts on another, it's going to hit it with a force, and then the reaction is going to be equal and opposite. So it's going to hit back with the same force, it's in the opposite direction. That means C. The force on the truck is the same in magnitude as the force on the car. It's just that the car, because it's smaller in mass, is going to have more damage. So 17. When a baseball is struck by a bat, the force of the bat on the ball is equal and opposite to the force of the ball on the bat. This is an example of, and we just said that, Newton's third law, equal and opposite force. All right, if you exert a force, F, on an object which has much greater mass than you do, the force which the object exerts on you will, remember, we just talked about the truck and the car. The truck had a greater mass, but they still had the same exact force magnitude. So we know it's not going to be these three. And Newton's third law says it's going to be in the opposite direction. So that is B. All right, number 19. A lot of these you're going to see is the same. Newton's third law refers to action-reaction forces, so those are the one object acting on the other object. These forces always occur in pairs, and they're going to be acting on different objects. So it's going to be D, because if my hand touches a piece of paper, the piece of paper has to touch my hand. It's not going to touch itself. Number 20. Same thing, this is a definition. Action-reaction forces are equal in magnitude and a point in the same direction. Equal magnitude and point in opposite direction. Unequal, we know all these unequal ones aren't right, and they're not going to cancel each other out. So they need to be equal in magnitude and point in opposite direction. Action, reaction. 21. A car traveling at 40 meters per second strikes a mosquito. Which of the following is a true statement? This is just like the car and the truck. So they're going to have equal force, but in opposite directions. Obviously, none of these answers are asking about opposite direction, but if we look, greater we can cancel out, smaller we can cancel out. And now they're talking about damage. Did they say anything in the question about damage? No. They're talking about forces, so it is B. Because the damage wouldn't be the same because the mosquito is much smaller. 22. The earth pulls down on a railroad wagon with a force of 200 kilonewtons. Which of the following is the reaction force? Well, if we know the action is the earth pulls down on the railroad wagon, then we know the same thing needs to be the opposite, that the railroad wagon pulls up on the earth, and they have to be the same exact force. So, it would be A. Railroad wagon pushes down on a railroad with a force of 200 kilonewtons. Which of the following is the reaction force? Again, you just turn it around to be the opposite. So instead of railroad, oh, it should be rail car. Or wagon, okay. Wagon, excuse me. Wagon pushes down on railroad. Opposite would be railroad pushes up on wagon, and it would be the same magnitude. So, let's see. All right, 24. Same kind of question. Earth pulls downward on a pen of mass m, which is sitting on a table. The magnitude of the force is mg. If this is called the action force, what is the reaction? So Earth pulls down on pen. That means pen pulls up on Earth. So, let's see. That would be B. Earth, pen pulls up on Earth. Number 25. A traffic light is suspended from a cable. Earth pulls down on the traffic light with a force of 1,500 newtons. This is the action force. What is the reaction? So, Earth pulls down on traffic light. That means we need traffic light pulls up on Earth. So that would be C. And it's with the same force, 1,500 newtons. 26. Soccer player kicks a soccer ball with a force of 1,300 newtons. The soccer ball then hits the player at the same time with the force of, we know that they need to be equal because it's equal and opposite reaction. So exactly 1,300. 27. Mass and weight. Mass and weight. Remember, mass is in kilograms and weight is in newtons. And you know that weight equals mass times gravity. So would they both have the same units? No, obviously not. They both have different units? Yes. Do they both represent force of gravity? No. Do they both represent the measure of inertia? No. We know the answer is acceleration due to gravity is higher on Jupiter than on Earth. So G on Jupiter is going to be greater than 9.8. The mass and weight of a rock on Jupiter compared to that on Earth would be, well, we know mass never changes, so we know the mass needs to be the same. So we can eliminate these two. But now when we talk about weight, weight equals mass times gravity. And if this gravity is now going to be higher and going up, that would make this answer higher, which would mean it would be the same mass, more weight. 29. Which of the following is an example of a force which acts at a distance without contact? Well, we know tension's with rope, so it can't be that. Gravity doesn't touch and it acts at a distance. Friction, both kinds, there's going to be touch there. And the normal force is balancing something out, so that's not going to be it. So it's got to be gravity. 30. Ball's thrown straight up. At the top of this path, the magnitude of the net force acting on it is less than 0, between 0 and mg, equal to mg, greater than mg, or none of the above. Well, if we remember when you throw a ball, at the top, the velocity equals 0. If velocity equals 0, that means that it's not accelerating at that point. So, sigma f equals ma, and if ma is 0, sigma f has to equal 0. But now if we think about the free body diagram for this object, we've got mg down, right? And we have the normal force up because it's not going up or down at that point. So, and our acceleration at this point is 0. So, Fn equals Fn minus mg would equal 0. So we have to add mg to both sides. So Fn, our force, equals mg. So that would be C. Hammer and pebble are dropped simultaneously from the same height. Neglect air resistance. So, does the hammer accelerate faster because it's heavier? The hammer accelerates slower because it has more inertia? The pebble accelerate faster because it has a smaller mass? They both accelerate at the same rate because they have the same weight to mass ratio? Or does the pebble accelerate slower because it has a smaller mass? We know that when anything's in the air and just dropping, our acceleration is equal to g, which is equal to 9.8. And if we think about in terms of ratio, W equals mg, g is the thing that would change it. So, g. They're going to accelerate that same rate of g because that is the ratio. 32. An elevator of mass m is pulled up at a constant velocity by a cable. What is the tension in the cable? We make our free body diagram. We've got mg down and mg down. You have the tension from the cable going up. And at this point, it's a constant velocity. So that means that your A equals 0. So if we make our sigma f equals ma, we know our sigma f is ft minus mg, and our ma is going to be 0. And if we add mg to both sides, our ft equals mg. So C. Now they're talking about the same elevator again, but now it's has a positive velocity, but it's decreasing. So if we have mg down, and the cable for the elevator goes up at ft, and if it's a positive velocity but it's decreasing, that means it's decelerating. So acceleration is going down, it's slowing down. That means our acceleration is down, it's negative. So we have sigma f equals negative ma, because the acceleration is going down. So ft minus mg equals negative ma. Add mg to both sides. Cancel that out. So ft needs to equal mg minus ma. So if that's your answer, can it be equal to mg? No, because you're still subtracting ma. Can it be greater than mg? No, because you're subtracting from it. All right. Can it be 0? No, because it is moving. So, can it be less than 0? No, because you wouldn't go less than 0. That means it needs to be between 0 and mg. Because if it stopped accelerating, then it would be mg minus 0, would just leave you at mg. And if you took out the whole amount, then it could be 0. So, between 0 and mg. It can't just be 0, and it can't just be mg. Now the next one's the same thing, but now it's increasing velocity, so it is accelerating. So we start with our diagram. But this time A is going up. It should say ft, I apologize. Now you've got sigma f equals positive ma, ft minus mg equals ma. Add mg to both sides. So now you have ft equals ma plus mg. So, can it be less than 0? No, because we're doing addition. Can it be between 0 and mg? No, because we're adding to mg. Is it equal to mg? No, because we're adding to mg. Can it be 0? No, because we're adding. So, it needs to be greater than mg. All right, number 35. 2 blocks are attached by a compressed spring, over here, initially held at rest on a frictionless surface. The blocks are then released simultaneously. If block 1 has 4 times the mass of block 2, so this is 4m, this is m, which of the following quantities is the same for both blocks as the spring pushes the 2 blocks away from each other? So, if you think about it, would they have the same speed? Probably not, because this one would probably go out faster. And the speed is the same thing as the velocity. Acceleration, again, it might fly out faster. Displacement, you can't really judge. And they would not be equal, because this one would probably move further away. So we're left with the force. And as we know, equal opposite forces. The force is the same, it's just a smaller mass would react a lot bigger than the other one. All right, 36. A block of mass 4m can move without friction on a horizontal table. This block is attached to another block of mass m by a string that passes over a frictionless pulley. If the masses of the string and the pulley are negligible, so the masses don't matter for the pulley and the string, what is the magnitude of the acceleration of the descending block? So if we think about it, this one, if we make our free body diagram, has 4mg down and fn up, and then ft to the side. This one has ft up and mg down. This one would accelerate down, and this one would accelerate to the right. So, we start with sigma f for each one. For the first one, we would get sigma f equals ma would be just ft, because it's the only thing in that direction, equals 4ma. For the second one, you would have sigma f equals ma, and you would get ft minus mg equals negative ma. And to get ft by itself, you'd add mg to both sides. You get ft equals mg minus ma. And since now they both equal ft, you can make them equal to each other. So 4 ma equals mg minus ma. So we want to move both MAs to the same side, so we add MA to both sides. So now we have 5MA equals MG. And to get the A by itself, we would divide by 5M, divide by 5M. And now you would get that A equals G over 5. All right, number 37. The locomotive is pulling an empty freight car with a constant acceleration on a horizontal surface. The mass of the locomotive is 5 times the mass of the car. Which statement is true about the force applied by the car and the locomotive? Again, this is the action-reaction, so that means they're going to have equal force. Doesn't matter what the mass is.